It's time for us to start a new topic of the vector calculus called the integrals. But it's not just the integrals you might remember from previous courses of engineering mathematics, like the definite integral or even multiple integrals, which are normally either straight lines or simple boxes in a Cartesian coordinates. This time we'll be talking about integrals along the curves, over the surfaces, or even volumes. And they're very practical in fluid mechanics, in engineering applications, and also, of course, for the electric and magnetic processes which we want to model. And you'll see at the end how these equations are useful for estimating fluxes of electric field or magnetic field and so on. But let's just do an introduction, an overview of what all these integrals are about before looking in more detail how to calculate them. We'll start with line integrals, which are integrals along lines. Let's think about the line. So you have a line, and you can move from A to B, and you can split it into small elements, delta r. Each of them have a direction as well as the magnitude. And if we divide this curve in these elements and then sum it up, we will get the length with also orientation, right? This whole curve from A to B. So if we'll go from little bits and then sum them up, you just get the vector connection A and B. Well, but that's fine. What about reducing the size of each of these elements to nearly zero, so what we call infinitesimal, and then this sum tends to become an integral. And this integral is an example of the line integral, where we call curly C the path of integration, or the line of integration. So this is the curve along which we integrate. But it's rather boring integral because it just gives you the length of the vector connecting A and B and also its orientation. So you just get a vector connecting A and B. So it's not particularly exciting integral. What is much more interesting if we'll take a field, let's say a scalar field, and multiply it by these elements and then sum them up. And in this case, we'll get another integral as we tend these little elements to zero. And that will be a line integral of the scalar field along this curve. And the integral itself is a vector. So both of these integrals so far were vectors, because we took a vector, multiplied either by 1 to get the vector or by scalar field, and then sum them up. So that will be vectors. Now, what if we take a vector field rather than a scalar field? There are two ways we now can define a product, because we remember for vectors we have two products. One is the scalar product, one is the vector product. Well, let's start with the scalar product. So again, summing up these elements in the limit, we'll get an integral, and this time the integral will be a scalar, a number. And that is what is called a scalar line integral of the vector field along the line curly C, or the path of integration. And that is the common definition which we will use in this course unit. So that is how the line integral in the majority of our station looks like. And another way, just for reference, not what we really encounter, is to use the vector product. So that time we'll have a vector formed by the vector field and the little elements, and as we sum it up and tend these elements to become infinitesimal, then it will be another integral, which is a vector integral. But that's not commonly used. So it's a vector line integral of a vector field. How are we actually going to calculate these integrals? Without going into details now, because we'll consider it much more carefully later, but still, just an idea, we need to know how to go along this path of integration, along this line, this curve. And for that we need often to parameterize it. So we use a parameter to describe where we are on this curve. Like, think of a time. You travel along a winding road, and at a given time you're at that point, then you later on move on to a new point, and so on. So that time is a parameter. Likewise, if you recall, there is an equation of straight line. You can describe it using an equation where you have a constant vector and another vector along this line, and then you sum them up with a parameter, and you can define where you are along this line. And the t here will be the parameter, and a and d are just constant vectors. And r is your position on that straight line. So normally we need one parameter for the lines. Now, the surface integrals are talking about surfaces. So let's think we have a surface, and we split the surface into little bits. Each of them have orientation. So we have one bit, another bit of the surface, and all of them have some orientation. And normally we will be talking about normal orientation to the surface. So think of this surface will become kind of like a hedgehog with a little orientation around it. And how we define this orientation? Well, there are multiple ways, but the most conventional one is to take a direction normal to the surface. And if the surface is closed, it means like it's a sphere, you take a vector which protruding normal outwards of the surface. If the surface is not closed, then you normally take a direction which still looks outside the convex side of your surface. And then if you sum up these oriented little surfaces, little elements, you'll get a total surface of your surface, which is also a vector because each of them has orientation. And if it's a sphere, then it actually will be zero because I cancel everything out. But it's again not particularly exciting type of integral. Let's look instead for a scalar field. And in this case, if we'll sum up, like we did for the line integrals, the scalar field with the elements of the surface, we get a vector. Right? So we split it up, take the sum of these products, then tend these elements again to become smaller and smaller, and in the limit we'll get this integral. But again, this is not very commonly used, so let's instead think of a vector field, because ultimately we're talking about vector calculus. And then again we have two ways. So let's think of a scalar product. So again we take a scalar product of the vector field with a little element of the surface. We tend this element to become smaller and smaller, and then we get this integral. And you can see that because it's a scalar product, we'll get a scalar, which is a number. And that is the integral we'll be using most of the time. So that is the most typical form of the surface integral. There is another one again for reference. If instead you'll take a vector product, you will get another type of surface integral, which will be a vector. But that's not you'll see commonly. And again, to calculate these integrals, we need to describe our surfaces. And the most convenient way to describe them using the parameters. But this time we need two parameters. Why two? Because think of you living on the plane. You have x and y, but then you are on the surface, you have two parameters, 2 degrees of freedom, like longitude and latitude, for example. And you will end up with the double integrals. Okay, so let's now discuss volume integrals. So volume integrals deal with volumes, and that time we'll split our volume into small bits, delta v. They don't have orientation this time, just little volumes. And if we sum them up, we'll just get the volume of this area, right, we considered, which is again nothing to be excited about. But what if we take a scalar field and multiply by these little volumes and then tend them to become smaller and smaller until they're infinitesimal, and then you'll get an integral, and the integral will be a scalar. And that is the most commonly used definition of the volume integral. But it's not the only definition. We can also take a vector field and again multiply by the little volumes, and then we'll get a vector instead. That's also possible, but we'll mostly deal with the first type of definition. Then we take a volume integral of a scalar field. So to summarize, we'll get the line integrals normally of the vector field scalar product with a little element of the line. Likewise, for the surface integrals, we get a vector field scalar product with a little element of the surface, and for the volume integrals, we will get a scalar field and just integrate, dividing our domain into small volumes. But what about how we can compute these volume integrals? Again, briefly. So then we have a traditional Cartesian coordinates where things are just parallel to the axis. Then our volume dv is just the product of these little elements in the x, y, and z directions. So that you've seen before. But now we can consider much more general cases where our domains, our volumes, are not like boxes, but can be anything. And in these cases, it's convenient to choose curvilinear coordinates such as cylindrical polar coordinates or spherical polar coordinates to describe these little elements of the volume. And even though they're expressed in a more complex way, these elements, it will lead to triple integrals. So later we will consider how to calculate these integrals in more detail, and also how they're applied to model electric and magnetic processes.